All right. So now we're going to make an ensemble learning with a random forest. So first we're going to make some data. This is going to be another one of those moon-shaped data sets. Yeah. All right. Nice of Google to give me all this free service. Okay. So there's a data set where I have blue things in a curve up the top and green things in a curve at the bottom, and they overlap. So you cannot perfectly separate them. So now we're going to make an ensemble. And what we're going to do is three different predictors: a logistic regressions, a support vector machine, and random forest. And a random forest is, I think, just those decision trees, but random parameters, where you don't even bother to optimize it. You just make a decision tree with random just if statements on the parameters, and that has some tendency to succeed, and you just make a lot of them. So that's the game here. It's going to use, but this one's going to combine three different predictors. So just want to see if I can understand a little bit more about the random forest. Yeah, random forest classifier. There's random forest, random state equals 42. Okay. I think the random forest automatically has a bunch of those decision trees it's combining, but I'm not quite sure. I've got a lecture about it, but I forget the details. Anyway, so now we combine three different things. So these are the three predictors. This one's 86% likely to succeed, 89 and 89. And when you combine all three of them, they're 91% accurate. And this is the point. Just like if you combine different measurements of something, if they're independent measurements, the noise will tend to cancel out. So that's the game here. Now, this classifier used hard voting. Each predictor will predict, and the one that has the highest output score will win for each instance. And that is, of course, kind of foolish, because the other ones, even though they weren't the one that had the highest signal, still have some information in them. So it would be better to do soft voting, where each predictor produces a probability, and you average the probabilities. So you really get the full value out of each of the models you're combining. And so now we get up from 91 to 92%. Now we can do bagging, which is where you make many random samples of the training set to train predictors on. You're just trying to create predictors that have some tendency to get the right answer, but are different. So the perfect thing would be to keep getting more data and train it, but you only have so much data. So what you do is you make random samples of a training set and train them on different random samples, so they will be different. And then when you combine them, the noise will hopefully cancel out. So we're going to make a forest with 500 trees. Right, 500 decision trees and combine them together. I'm amazed you can do this with any reasonable amount of computation time, but you can because the decision trees are so simple. So here, a single decision tree is on the left. This is what it did. And you see it found a border, but it had some crazy, tried to hit this spike here. That's what a single decision tree did. And you see it kind of fit the noise more than the sample. And when you do bagging, 500 decision trees, you actually do a really good job of drawing a nice border to separate these things. So that's the game. And then we can do ADA boost. This is adaptive boosting. This is another way to combine many machine learning models to make them better. And what you do is you make one machine learning model to fit the data, and then you take the variance. So you take the errors from that one and fit it to another learning model, and then you take the errors from that one and fit it to another. So you make successive approximation. That's the game. That's called ADA boost. And so what you have here is, I think this is the this is the first one here through this terrible boundary that after two cycles, that was the first fit. Then it added a second one to correct the errors in that and got here. Then it went to a third one way over here and a fourth one way over here and a fifth one way over here. So instead of converging, this is with a high learning rate. So it makes big jumps. And so the jumps are too big, so you don't find the minimum. You jump over the minimum and back and forth. If you try to learn too fast, you overshoot. This one, you have a more modest learning rate. With a slower learning rate, now you can see it sort of converges to a good solution. And this is another fundamental parameter, all machine learning models. Remember the original one we did, we had 500 steps to reach the bottom. You take little steps and you reach the bottom. And this is something that the machine learning models work hard to optimize, is how big are the steps you should make in changing parameters so that you make progress towards finding the bottom, but you don't jump over the minimum and miss it. All right. So that is the ensemble learning and random forests. Let's stop this one.